And the effectiveness of disinfection depends upon what it is that you're trying to inactivate or kill, and how much you apply, how much of the disinfectant you apply, and how long you apply it for. So the WHO suggests that after you've disinfected the water, it should have 0.5 milligrams per litre of chlorine still in it, having been disinfected for 30 minutes. You multiply those two together, you get what we call a CT value of 15. And what we've got here are various CT values for killing E. coli, polio. And you can see that most of them, down to rotavirus, all fit in within the CT value of 15. It's Giardia and Cryptosporidium that don't, but we don't use disinfection to remove these from our water. But the point of that slide is just to say that your disinfection efficiency relates very much to what it is that you're trying to get rid of and how much chlorine you're adding for how long. Right, my only bit of chemistry for this evening. Anything else is too complex for me. We know that when we add chlorine to water, we produce hydrochloric acid and hypochlorous acid. Depending upon the pH of the water, that hypochlorous acid will dissociate the hydrogen ion and the hypochlorite ion. And so we've known that for a long time, and for 60 years, post the work of Snow, we were adding chlorine to water, thinking it was this global panacea for water treatment. In the early 1970s, there was a Dutch chemist, Johannes Rook, who was actually investigating sources of odour in water. And Rook applied Rook was looking for things that might give rise to the odour in water. He was looking for volatile organic compounds. And in doing so, in the early 70s, he actually found in a Dutch water coming out of Dutch water treatment works, he found chloroform. So he went to the head of the works, to the raw water, and found there was no chloroform there. So it could obviously be concluded that the chloroform had come about as a result of the treatment processes. And it had been identified in the post-war years that exposure to chloroform was carcinogenic in rats and mice. So although the quantities, the concentrations of chloroform that Rook and independently Tom Bella found in the United States, although these concentrations were very small, finding chloroform in the water was of a concern to them. Sort of irony about this in that John Snow was promoted to the physician to Queen Victoria and administered chloroform direct to her as pain relief in childbirth. But come the 70s, we were aware that there were potential downsides to chloroform. So what Rook and, say, independently Bella and his colleagues found was that if you take chlorine, hypochlorous acid, and add it to water which has got natural organic matter in it, that's what the NON stands for, apologies for that. If you've got water with organics in it, then you will create low levels, some very, very small concentrations of things called disinfection byproducts. We're aware that there are hundreds of disinfection byproducts that are produced as a result of using all sorts of different disinfection techniques. In the UK, one of the standards that water companies must meet is associated with these things, trihalomethanes, THMs. And the group of THMs that water companies are tested on are listed here: chloroform, bromodichloromethane, chlorodibromometane, and bromoform. And the standard says that you can't exceed 100 micrograms per litre of the sum of all of those four. So that's a standard which the water companies have to meet. Now, the chemistry behind THM formation is complex, but conceptually it's quite straightforward. We know that if we add a dose of chlorine to water, it will decay with time, decay exponentially. When we do that, we know that we will also create trihalomethanes, and they will follow almost the reverse process. We'll see a rapid formation of THMs, a rate of formation of THMs to start with, and then a slow levelling off. Just to prove that to you, we've done it hundreds of times in the lab. Chlorine on this axis here is the blue line, so we added just over 1.5 milligrams per litre of chlorine to water that we took from before disinfection from the water treatment works, and you can see it decay over 4 hours down to about 12 milligrams per litre. And at the same time, you can see the response in THMs, the trihalomethanes. After 4 hours, we've got about 36 micrograms per litre. Bear in mind the standard is 100. So everything looks okay at this point. Let's take some data from a water treatment works. The yellow spots are real data. THM concentrations on the vertical axis, and we've got 5 years worth of data on the horizontal axis. Not many data collected in this area here, but they're more here. And the first point to note is you can see this seasonal variation in THM concentrations, and that's because we know that THMs are formed quicker to a greater concentration rather in hot weather. And so you can see that at this water treatment works, it was in the summer periods, THMs going out into distribution were around about 60 micrograms per litre. However, I said earlier that water companies have to maintain a residual, or choose to maintain a residual in the distribution system, so the water doesn't become reinfected. So there's chlorine in the system, and there's still organics in the water as well. And so what one finds, if one moves further downstream in the system, then the THM levels will rise because there's still reactions going on, and they'll continue to rise until you get to the end. Well, they'll continue to rise until the chlorine is depleted or the organics have been depleted. So you can see that if we have a statutory limit of 100 micrograms per litre, water industry, naturally and understandably a risk-averse industry, doesn't wait for it to get to 100 micrograms per litre. I don't know what the situation is here, but other companies would operate a trigger level of around about 80 micrograms per litre. So if we measured 80 micrograms per litre, that would start companies thinking THM levels are quite high. We should be doing something about it. And so you can see here in my example that we've got a number of data points clustered around there. So the challenge for water companies and for researchers such as myself is to reduce the levels of THMs in our drinking water. Albeit it's a very small concentration that are there already, we try and reduce them further. And how do we go about doing that? Well, I think the obvious thing to say is that if that much chlorine creates that many THMs, and actually you want to create that many THMs, then surely the obvious thing to do is to reduce the amount of chlorine that you add. And indeed, that will reduce the amount of THMs in your drinking water. But what it will also do is increase the risk of reinfection of that water in the distribution system. And so companies find that they have this balance to be struck. A total THM target of, it's not a target, a ceiling, of below 100 micrograms per litre, whilst also conscious of the need for water not to be microbially compromised, to maintain a chlorine residual of between 0.1 and half a milligram per litre. So in order to do that, what we need is perhaps some different treatment technologies. And in the 36 years since Rook and Bell et al. Published their papers, believe me, there has been a lot of work on reducing THMs. And one of the ways it's focused on is removing the organics. If we still have to add disinfectants, let's remove the organics, because then that will reduce the concentration of THMs. There's been a whole raft of work done and still ongoing on enhanced organics removal. For example, we know that organics removal is enhanced as